This discussion is over section 7.6. We're going to kind of look at double integrals and remember when we had functions of one variable. And we're not going to go into this as deeply as the book does, but I just wanted to talk about this a little bit so you can kind of see, we spent all this time in chapter 7 talking about how do I take derivatives of functions of several variables. Well, it's only natural, I'm sure you've been wondering for a long time now, to ask ourselves, well, how do I do this? How do I integrate? That's why we're talking about double integrals. How do I integrate now a function of several variables? So look at what I have drawn here. So this, remember, back when we were, living our lives in a world where all functions were of one variable. And then we expanded our viewpoint to know that there are functions of several variables out there. But before then, what did this definite integral give us? The definite integral, one of the things it gave us, now remember we have lots of things that the definite integral gives us, but it gives us the area underneath the curve, right, from A to B. So if you think about this, basically what you're doing is you're integrating over one dimension, right? A to B is one dimension. And then what is this spitting out? It's spitting out something that is in two dimensions. So likewise, if I have several variables, if I have a whoa, Sarah, settle down. If I have a function of several variables, okay, remember now, if I have a function of several variables and I graph this function, so f of xy, then z equals f of xy, I get something that's three dimensions. So when I integrate this, what we're going to see is we're going to have a double integral of this function because now I'm going to put dy dx, but it doesn't matter. It could be dx dy, okay? And what this is going to give us, now not only am I integrating twice, what I'm doing then is I'm looking at this dy dx, so maybe I'm taking something in the y direction, and then I'm also looking at how does this guy expand in the x direction. And so now instead of going over a one-dimensional interval, I am looking at what is this function doing over a two-dimension interval. So I'm going to go from 2 dimensions now into 3 dimensions. And what does that give us? That gives us volume. Now again, we're not going, let me draw a picture. Oh, this is a bad picture. You should look in your book. See, and then sometimes I just can't stop and I want to try and make it better and it doesn't make it any better. But anyway, so there's the, maybe it has like a rounded top. I should just stop it, Sarah. So anyway, this is what it gives us. It gives us volume. I'm not too worried. We're not going to spend a whole lot of time. You can get into this a little bit more deeply on finding volume. We really are just going to focus on how do I take a double integral, just in case someday you need to know how to take a double integral, just the real mechanics of doing it. And then we'll move on, and we're going to move on to chapter 9 after this. But so I'm just going to do some examples for you. That's really all this is going to be. And I know I've said this before, but I think this might be a short video, but we'll see what happens. Okay, so for example, let's do something like this. I'm going to take the double integral from 1 to 2, and then from 3 to 5 of this function of several variables, x plus y. We're going to start off pretty easy, and then we're going to do dy dx. So what do these numbers mean? Well, what this means is, if I look at my axes here, in the y direction, so look at what's going first, dy, and so what's applying to dy first? You can almost think of this as being kind of two integrals, like this is my first integral, and then I do my second one. But what is this saying? This is saying that y is going to range from 1 to 2, so I know y is going to range from 1 to 2, and then if you look out here, x is going from 3 to 5. 3, 4, 5. So x is going to range from 3 to 5. So what is the area that I'm integrating over? It looks like I am integrating over this area right here in the xy plane. And then whatever x plus y looks like, that's actually a plane in 3 space. But wherever that's at, then I come up here and I basically grab, that chunk of whatever. I think it's a plane. Whatever that plane is here. Oh, I need to stop drawing 3D. All right, so what I care about more is, do you know how to do it? Okay, so let me show you what we're going to do. So what I'm going to do is I'm going to evaluate this first integral that I have in yellow here. So I'm going to rewrite the 3 to 5. Good notation, right? You are in Calculus 2 now. I expect good notation. And you might expect, I mean, we know how to take the partial with respect to y, right? We treat everything as a constant, and we take the derivative, like, not everything, excuse me. We take everything that involves x as a constant, and we take the derivative of y just as y. So likewise here, when I'm integrating, what I'm going to do is I'm going to treat x as a constant and then take the antiderivative of y. So let's think about the antiderivative of x. Well, if I was integrating like 4 plus y dy, I just want to show you an example. What would the antiderivative of this be? So now get away from derivatives, go back into antiderivatives, excuse me. The antiderivative of 4 would be 4y, and the antiderivative of y is 1/2 y squared, okay? So this is just an example here of what we do to a constant when we take the antiderivative. So same thing up here, what will this x become? It'll become xy, right, plus 1/2 y squared. And then what am I evaluating this from? I'm evaluating this from 1 to 2. And then I still have my dx there. Please notice I'm using good notation here. I have the 3 to 5. It stays with me because I haven't used it yet. Okay, you can't just drop that and bring it back in whenever you want. You have to have good notation. And then what is all this in here? This right here is all this yellow stuff here. Now I'm going to simplify this. These are kind of fun, actually. I know we have different ideas of fun. And, you know, if you took the derivative of this with respect to y, you see you would get x plus y, right, which is what we would want. So how do we evaluate a definite integral? We plug the 2 in, so we would get 2x plus 4, it looks like, because 2 squared is, no, divided by 2. Come on, Sarah. All right, 4 divided by 2 is 2. Then minus, plug in the 1, I just get x plus 1/2. And then I still all have dx. So if you notice, what I'm doing there is I'm working with this definite integral on the inside, and I still have this other integral on the outside. So I simplify, clean this up a little bit. We get 3 to 5. 2x minus x is x. 2 minus 1/2 is 3/2 dx. And now I just have a pretty simple integral with respect to only one variable, which is good. So I have 1/2 x squared plus 3/2 x evaluated from 3 to 5. So we know how to do this. Put the 5 in. That's 25/2, right? Plus, put the 5 in again. That's 15/2 minus parentheses, right? 9/2, yeah, plus 9/2. Cool. So this right here is 40 over 2, which is also known as 20. This is 18 over 2, which is also known as 9. And we get our answer to be 11. And again, what does that 11 mean? That would be the volume of whatever this three-dimensional object is. So that's one way we can integrate. We can integrate over a nice little like square or rectangle. And when does that happen? That happens when my bounds are constants, okay? So let's look at an example then where my bounds aren't constants. Okay, so now I'm going to integrate from -1 to 1, and then 2x squared to 1 plus x, and let's integrate x plus 2y dy dx, okay? All right, so let's see what happens here. So now if you look at this, what is the difference here? Well, the difference is I don't have constants. So what this is saying here, and notice I have the dy again. So this is my y, this is my x. If I look at what these bounds are, well, in the y direction, I have the line 1 plus x, right? So at -1 and 1, so here's my line 1 plus y equals 1 plus x. And then I have y equals 2x squared. So at 1, it'll be up at 2. At x equals 1, it'll be up at 2. 2x squared is just a parabola, right? Okay, and so in my y direction, I'm going to be integrating on this, and then in the x direction, I'm going from -1 to 1. So I'm doing this bounded area right here because they meet at, well, they don't meet at -1 and 1. But if I look at 1, so we're going to meet, it'll probably be more like about like this bounded area right here because x is restricted from -1 to 1. It's probably not perfect, but you know what? It doesn't have to be. Really, people, what in life is perfect, right? All right, let's take the antiderivative of the inside. Again, if you want, you can put kind of parentheses around this part so you can kind of focus on what you're going to integrate. And I'm going to integrate with respect to y. So again, I get an xy, and the antiderivative of 2y is y squared, evaluated from 2x squared to 1 plus x dx. A good notation. Don't be lazy when you write math, okay? Now I'm going to plug in this 1 plus x in for y, because that's what we just integrated with respect to. So 1 plus x plus 1 plus x squared minus, right? Now I'm going to plug the 2x squared in. So if I plug the 2x squared in for y, that'll give me 2x cubed. And if I plug the 2x squared in for y squared, right? So I have minus, if I square that, I'll just go ahead and do that. I get 4x to the 4th, right? And then all of this dx. And if you want, you can put these big parentheses on them. So I hope that makes sense, okay? All right, so I need to simplify all of this. So I'm going to do a little bit of work here. So I get x plus x squared, and then I'm going to FOIL this sucker out. So that'll be 1 plus 2x plus x squared minus 2x cubed plus 4x to the 4th, okay? So just simplified that a little bit underneath, and now I'm going to rewrite my integral. So -1 to 1, let's see, x squared's there, I get, well, actually, okay, I have some issues, and I know you probably don't care, but I really, really need to write this in descending order. You know, I just have some issues that I should probably, you know, get checked out, but it's okay. So you'll just have to deal with them. So I've dealt with that, dealt with that, dealt with that, dealt with that. 2x plus x is 3x, and then plus 1 dx. Whew! Holy moly. All right, people, now let's take the antiderivative. Who came up with this problem? I think I did. Maybe I should think about that. Add 1 to this, I get x to the 4th, and then 2 divided by 4 is 1/2. X to the 4th plus 2/3 x cubed plus 3/2 x squared plus x evaluated from -1 to 1. Whew, goodness. So I'm going to plug in 1. That'll give me 4/5 minus 1/2 plus 2/3 plus 3/2 plus 1. And then I'm going to plug in a -1. Now the negative, anytime I have an odd exponent, that's going to make it negative. So -4/5, but anytime it's an even exponent, it'll just keep it the same. Minus 2/3 plus 3/2 minus 1. Okay? Oh, man, and I don't want to do that. So I'm going to let you do that. So, well, let's look. Let me just give you kind of some hints here. So look what I have here. I have 4/5 plus 4/5, right? So that's 8/5. Here I have a -1/2 plus 1/2, so those 1/2s are going to cancel. Here I get 2/3 plus 2/3, so this isn't too bad. 4/3. These 3/2 are going to cancel because I get 3/2 minus 3/2, and this becomes 1 plus 1, which is 2. And then if I get a common denominator, my common denominator is 15. So 8 times 3 is 24. 4 times 5 is 20, and 2 times 15 is 30, and this will all be over 15. That's kind of a trick for doing these. And then I'm sure in the back of your mind you're like, Sarah, I'm going to use my calculator, which is fine too. So I think the answer is 74 over 15. You know, I think that's close enough. Don't you think that's close enough? Yeah, good enough. Okay, so I hope that makes sense. Let me do one more example and then we'll call it good. How much? Yeah, see, I told you this was going to be a fast lecture. I'm very proud of myself. But if I keep like talking, What I'm just looking for, I want to find you one. I might actually do one of your suggested problems for you, because I would like to find you one. In my notes, I don't have any that involve E. So, yeah, I'm going to do a suggested problem for you. So I'm going to do, and then of course, look on, the fun sheet has some examples also. So one example I want to do for you, this is from the fun sheet, and so it's it has constant, or not from this fun sheet, excuse me. This is from the suggested problems, this dy dx. And also I've done a lot of these that are dy dx. They don't always have to be dy dx. I think all of them in your book are, but you can do dx dy also. It doesn't matter, but that's okay. They can do dy dx, that's fine. I wanted to do one with E for you because the E is kind of interesting. So again, and looking in your book here, they actually do put parentheses around these guys. But again, you don't have to do that. I'm not sure why they do that. If I complain so much about the book, maybe I should just write my own, right? I don't think I'm gonna do that. All right, let's look at this. X e to the xy. So if you get stuck and you're like, wait a minute, I don't know how I'm going to do this. Let's think about, remember, x we're going to treat as a constant. So what if this was 2e to the 2y dy? Well, think about this. The antiderivative of e to the 2y is e to the 2y over 2, right? I divide by the derivative of the exponent, and then this 2 just hangs out. So if you notice, these 2's cancel. So sometimes it's nice to go and try it with a constant, see what's going on with the constant, and then come back and apply what you've just done over here. So here, do you see these x's are just constants? So when I take the antiderivative of e to the xy, I would get e to the xy divided by x, so my x's cancel out. Isn't that cool? Love that. What a great example. Okay, now maybe I do like the book, right? I just praised it for what a cool example it was. Now I'm going to plug the 1 in to the y. So then minus e, plug the negative 1 in. I get a negative x dx. Now I'm going to take the antiderivative. We love e, right? It's so easy. I crack myself up on these videos, and I'm all by myself in my office. So maybe I have more issues than I even realize. So here, look at the antiderivative of this. I'm going to take the antiderivative, and what is it going to involve? It's going to involve dividing by that negative 1, the derivative of the exponent. And so actually what happens is I get plus e to the negative x, evaluated from negative 2 to 0. So let's put in, you must put in the 0. Remember, e to the 0 isn't 0. And then I'm going to have minus e to the negative 2, right, plus e to the positive 2 when I plug that in. So if you look at this, e to the 0 is 1. So this is going to be 2 minus e to the negative 2 minus e squared. All right, people, that's all I have for you today. I'm really proud of myself. Under 19 minutes. So these are kind of fun. I hope you enjoy them. If you have any questions, as always, shoot me an email and let me know what I can do to help. All right, you guys, enjoy.